Thank you everyone. Good morning. Welcome to this talk. Just before we get started, I've added a short link to the content here. I'll show it again later when we actually need it and when we're gonna start working on the exercises. I see a few people without a laptop, so you might have to work with your neighbors or figure out something together. So yeah, the talk today, maintainable code in data science. So we'll try to write data science code a bit differently than just everything in a notebook and a list of comments there. So I hope you all had some good coffee. I appreciate that it's quite early in the morning. So we'll start with a little bit of philosophy and try to define, well, what do we even mean by maintainable code? Does someone want to start with a definition? Nobody? So I'll give mine directly. It's early. So my definition would be just this, really simple. By maintainable code, the main thing that we expect is that it will be easy to modify. Like code has to be modified all the time. So maintainable code is the code that you hope can be easily modified. That can mean all sort of things, and that's what we'll see a bit later. Right. So one of there are many principles that exist in the software development world to help with defining what is maintainable code. One of them is the single responsibility principle. That just states that any function or class that you're writing should really try to do one thing. You shouldn't have a God function, a God class that is doing all sort of multiple things and everything at once. Instead, it should really be focusing on one thing and do it really well, and that allows to do all sort of nice things with it later on. So that's really what we'll try to keep in mind in this talk. But then in data science, it's a little bit more complicated. Like there are a lot of other constraints that appear there because of the nature of what we're trying to achieve. And that's also what we'll discuss here. So in order to do that, I'd like to first go through the main stages of a data science project. So you'll have, at some point, to process some data, to engineer some new features from existing data that you've got available. You will have to tune some hyperparameters of your model to try to find the best values. You will have to train your model on some data that you have already pre-processed, and after, you will have to generate predictions on new data. So let's go through all those steps and see what do we care about, what do we need to care about to make those maintainable. So for the first one, process some data. What we will care about is how easy it is to modify those pre-processing steps. So maybe you want to add some steps. Maybe you want to add a scaling step to your pre-processing pipeline. Maybe you want to remove some. Maybe you want to modify some. Maybe you'll have to change a little bit the way you get categorical features out of some complex data. So all of those, you should be able to do it as easily as possible if your code is maintainable. Then tune hyperparameters. So your data will change every time you will change your features and you will change your pre-processing steps. You will have to retune the whole thing. So you would hope that your way of tuning the hyperparameters and finding the best parameters for your algorithm is quite easy to run, and you can rerun it every time anything changes to get the best parameters directly and then retrain your model. Same thing for training your model. Every time you will change something in the data, or even if you don't change something yourself, the data itself will change over time. So you will have to you will need a good process to retrain it constantly. And finally, which I think is the most interesting one, generating predictions on new data. So here, you will have to do all the same steps that you've done in your pre-processing stage on the training data. You'll have to apply the exact same transformations, but ideally without repeating any code. Because if you start repeating code, then it becomes much less maintainable. You have to modify things in 2 different places at the same time. So how do you do that? That's something we'll see later in this tutorial. Actually, right now. So the first thing I'd like to talk about is how do you make your feature engineering data processing stage more maintainable. So again, let's focus a little bit on what we need to do here. So for pre-processing, you will need first to load some data. You will need to split into some training data, some test data. You will probably need to drop some features. You don't need everything there. You will need to clean some of them, so remove the null values. Maybe you'll need to remove some outliers as well, all sort of operations like this. You will need to engineer some features, so that's probably where all the creative part of the data scientist job comes in, where you take your old features and you figure out, well, how can I convert this data to have something that is more meaningful for my algorithm. You will probably have to apply one-hot encoding on the categorical features, unless you use an algorithm that supports categorical features. And that's usually one of the big problems. And you also have to, sometimes, depending on the algorithm you use, scale and transform the numerical features that you've got. Right, so quite a few things you can do on your data. So let's see. Let's take a closer look, maybe at number 6. So, how would you apply all those steps on both the training set and the test set? So how do you make sure you don't duplicate code here? So the first idea that would come to mind would be to just create a reusable function, apply that function on a training set, apply that function on a test set. Yeah. That's good, but what if that transformation needs to remember a state, which is the case for one-hot encoding, for example, for scaling, and those kinds of operations that learn something from the training data. So just to make sure we're all on the same page with that, I've got an example with one-hot encoding to make clear what I mean by that. So, say here you've got this training data with some countries for multiple people, and then you apply one-hot encoding on it. So that's what you get out of it. So country UK for the first row, country Italy, and then you have ones and zeros there. Now, if you want to do the same thing on the test data, if you just apply one-hot encoding again, so let's say we've got this data in the test, and sometimes you'll have just one single row that you want to apply this transformation on. Well, if you've got this data in the test and you apply one-hot encoding, that's the output you would get. So it would, from scratch, learn again the new columns that it needs to build, and build it in the same order as it appears in the test data. So that here, there's a big mismatch. That's something that you shouldn't do. And it's going to break your algorithm. So here, that's a good example of when you need to have a pre-processing steps that need to memorize some transformation to be applied later. And that's what we would have liked instead, right? We would have liked the same columns as the previous, as what has been learned on the training data, and mapped to the new data set. So here we see it actually that the first one, the row France, that wasn't in the training data, we've got a row of zeros, which is here what we want. Great, so in that case, we will need to build somehow a class that is able to save the state. And that's what the scikit-learn transformers will allow you to do, and it facilitates all all that process. So that will be really our main focus for this tutorial. Look at all those tools that are provided by scikit-learn that allow you to write code in a more modular way and overcome all those issues. Right, so some transformers that you surely have used in the past, so the label encoder, which is a famous one, the one-hot encoder, which we've talked about already, that I suppose everyone has used, the standard scaler as well, to do a scaling transformation. So all of those will have the same API, the same interface. They will have a fit method that just learns a transformation and saves it in its internal state. So for a standard scaler, it learns what is the weights of the scaling it has to do. And then whenever you call transform, it doesn't change anything in its internal state. It just applies the same transformation it has learned before on any new data. Right? So that's this interface that we'll reuse over and over again. Some other examples of transformers. So PCA is actually implemented as a transformer with scikit-learn. So it will have a dot fit method that allows you to learn the linear combination to go from your original features to the principal components. And then when you call dot transform, it doesn't learn anything again. It just applies that transformation. Another one that is maybe less known is the feature union. That is quite useful to build, to apply functions on some numerical data and get a new array with all the outputs. For example, here, feature union of PCA and polynomial feature will look like this. I've got a data frame with some value. I apply the feature union of PCA and polynomial features, and I get a new data frame with a lot of new columns that are generated from me. Some of them will be the output of the PCA. So here I keep PCA with n components equal 2, so I'll keep the 2 principal components. And then the polynomial features will just generate all the polynomial values for each of my columns in my previous data set. So here, that's interesting, because I've used this transformer that takes a list of other transformers as input and is itself a transformer that can generate this new data. So here, starting combining things together, and that's what we'll do more and more later in this tutorial. So now I'm able to generate 2 first components of PCA and polynomial features all at once. Then you can also build your own transformer object. So to do that, you will need to inherit from 2 different classes that are implemented for you in scikit-learn. So you'll have the transformer mixin and the base estimator. So those just contains some hidden methods that scikit-learn needs to work with your tools. And then all you have to do is implement the fit method and the transform method. And then you can use this class everywhere you want as a transformer object. So you could combine it with the feature union like we've done here, or with all the other things we will see later. If you need hyperparameters, and that will become really handy later, you can just add an init method in there, pass it some parameters, and use that as a hyperparameter later. Right, so here that's an example. I've got this custom scaler that I've built that, as I said earlier, inherits from the transformer mixin and the base estimator. It has here a fit method that is called on some training data, where it computes the median and the interquartile range of my training data. It memorizes it with the self keyword here. And then whenever I call transform, it doesn't need to learn anything anymore. It can take any data with the same number of columns as my training data, and we'll just apply that transformation here, which is removing the median and dividing by the interquartile range. Right? So that's super easy to actually build your own transformations like this that will memorize a state, whatever state you need. And in the exercise that we'll have coming soon, we'll do that together with some transformations that are really, really common to do on data. Actually, the exercise is right now. So if you go to the, so I can show again this URL. So if you go to that URL, that will bring you to GitHub repository, where you've got all of that, including here an exercise. So if you clone that repository, you can then open. What do you want? The URL, yeah. Sorry. Anyway, so once you've cloned it, you can then open in the exercise notebook. That is where all the instructions are. So that's not where we're going to write the code. It's where the instructions are. Okay, maybe give a minute to do that. You all good with the URL? Take that for yes. So multiple things I need to show here. So when you open the notebook, so here you have instructions. The first thing we will do here is set this notebook magic method, which I don't know if everyone has used before, but it's a really useful trick if you want to develop code in an editor or in another place and still load it in the notebook. So here, if I run those two commands, that will set the auto reload mode. That is whatever function I import from a file that I'm writing. If I modify the file itself, then the notebook automatically reloads the latest version that I've got. So I don't need to restart the notebook every time I make a modification in my file. So that allows me to live update the file in my editor and test it and prototype it in the notebook. So you get the best of the two worlds. So if I run that, here we've provided a function that loads the data set. Oops, that doesn't work. So you'll need to install joblib pip install joblib. We'll talk about this library later. How do you mean it's here? Mm-hmm. All right. So here. Still not. Anyway, I'll just uncomment that for now. Is it working for you guys? just going to uncomment that. What? Right, so in the meantime, whilst I'm solving that, I can at least explain what the exercise is. So here, what I'm fighting to load is the data set, so that's, yeah. I mean, here I'm just zooming on the error I'm getting. So here, what I'm trying to load is, well, actually, I can just load it with pandas to show you. No, but I just killed it. Yep. Right, so yeah, so that's what should have loaded with the command below. And if you have joblib and scikit-learn installed properly, that should work for all of you. So that's the data I'm trying to load. So that's the Kickstarter data set that is quite a common one in like machine learning competitions and things like that. So it contains some information about Kickstarter campaigns. So Kickstarter campaign can be launched on the website at a certain time with certain attributes. So here you've got information like the description, the name of the campaign they're trying to launch, the goal, so they're trying to raise money, so how much money they're trying to raise. You've got things about from which country they're trying to raise it, in what currency, and you also have the currency exchange rate, so you can actually try to convert from a currency to another. And you've got information about, again, the location, the category of the campaign, and all sort of information like this. And what we're trying to predict is whether that campaign will be successful or not. So we've got that information in the other file, ytrain.zip. So here, does that command run for everyone else but me? Great, so it's just me then. Perfect. So that's the first thing I wanted to explain. Then the second thing is we're providing some first skeleton for a model. So here what we've decided to do is divide our model into two main files. So you'll have the transformers here. That will be the place where you can define all your transformers objects. So here, all the pre-processing steps that we want to do, we are saving them in this transformers.py as a class with a .fit, .transform method. So all of those, we will implement it together. So here we see that we have one which is categories extractor, which is supposed to extract the category from the JSON.
Make the text bigger, please.
This one as well? Yeah. All of them. All right, so yeah. So here, this class here is a transformer that will allow you to extract some JSON that is contained in the category information here. So we'll take a closer look later. You've got this one. There is a goal adjuster that allows you to convert, that once we've implemented it, will allow you to convert a goal that is given as dollars into, all the goals that are given in anything else than dollars into dollars, using the exchange rate. You also have this other preprocessor transformer here that will implement that will just load some dates from the data and compute the difference between two dates to see how many days did the person live between, say, the launch of the campaign and whatever deadline they're working towards. And this one is a transformer that will allow you to extract the country from the data set and map it into a more larger area. So you can say, for example, here we'll group together all the countries in Europe. So those are the transformers that will implement. And there is a model.py, which is where you'll put all the things together. So here we've got that load dataset method that was a function that wasn't working for me that I'll fix in a second. Then you've got a build model function that we'll explain a bit more later, and other functions that work as entry points to train your model, etc. So that's for the general architecture of our model here. Now we'll focus on the transformers only. So if you take maybe 10 minutes should be enough to go through the part 1 of this notebook that explains how to implement all those custom transformers that I've talked about. So the category extractor first, and as you can see here in the notebook, we only have code to test your implementation, and the implementation itself is done in the file. So if you open the file transformers.py, edit it on this side, and then go to the notebook to test your implementation, it should all work perfectly fine. Right, so take 5 to 10 minutes to do that. In the meantime, I'm fixing my error. Perfect. All right, have it working. That's great. And let me know if you've got any question. So remember as well the main structure to build your own transformer. Something important here is that your fit method, even if you don't want to do anything in the fit stage, which is the case for the first few transformers we're building, it needs to return itself. That's just what scikit-learn expects. So if you don't have it return itself, you'll have some nasty bugs later on. All right, so let's try to do that together now. So the first one is the category is extractor. So as I explained earlier, this one is meant to read that field here called category. A bit further. That field here called category and extract a certain category out of it. So first, let me actually show that field a bit more. So if I do xtrain that category, you can see how it looks like. So that's some JSON, some string in a JSON format here. Let me just get the first one, for example. Oops. Why doesn't it go? Oh, because they're IDs. God damn it. Great. So that's so here. If you take a look at that, it will have this field called slug, which is the only one we care about here. That has this information. So the first part of the field slug will be our generic category for the campaign, and the second one will be a more precise category. So here we want out of this specific column, we want to extract those two fields. So let's implement a transformer for that. So here we're already providing two methods. The first one, the init, is actually defining a hyperparameter here that is useAll. There is just a trick that I added that allows to decide whether you want to create, whether you want to extract all the categories or if you want to extract only categories that you've hard-coded initially. So here the idea is that there might be so many random categories in all those JSON fields. So I've pre-selected the main ones that I was interested in. And then I've added a default for those that I'm not interested in. So if you look at the helper method that I've written here, that basically loads the file, loads the string here as using JSON into a dictionary. It's getting the slug method, and then it's getting the two different values as a tuple. And then here, I'm just saying that if you're not specifying the use all parameter, you will filter. So if the first category is not in your list of categories you care about, then you return a default. If your second category is not in your list of things you actually care about, you return a default. So it's just a way to make sure that we don't have too many dummy features later on. Right, so now we can implement our two methods that we'll need. So the fit method here, nothing to do. We don't need to learn any internal state. We just extract that information from the JSON. So here I can just do return self directly. For the transform, so for the transform method, I'll get the data frame, and I need to get the column category. So I'll call category equal X category, so it's easier to work with. And then I need to return a new data frame out of that. So I'll do return PD data frame. And this data frame needs a column called gen cat for the generic category. And that will be my category to which I apply I will apply a lambda that takes an X and returns self gets log. So it basically applies this method on each of the JSON strings and gets the first value here, right? So if I just do get slug X, and I get only the first value. Right, so that's here should work. If I run that, here the first column works fine. So I can now create the second column, which will be the precise, how did I decide to call it here? Precise cat. And that will be the exact same thing, but returning the second value instead. Okay. And here, if I run that, now I get my two columns, right? So that's pretty powerful. Here I've got a nice class that is easy to maintain. I can add more functionality there if I want later. I can change the way I'm computing those columns fairly easily by just modifying my transform method. So it's quite easy to maintain. And as far as I'm concerned, in my top-level code, I'm just calling this extractor always the same way, because it always has the same interface. So then the goal adjuster, so here, that should be fairly easy one. So same thing, I don't need to do anything with fit, so I can do return self. Here to transform, I just need to return a data frame that has adjusted goal, and the adjusted goal will be X. So that will be, let me check. So that will be the, where is it? The deadline. No, not the deadline. Where is it? the goal, where's the goal? The goal, so that will be x dot goal times static USD rate. Right, so that should do. If I run that, I get again what I was expecting. So I think you get the point with those. For the time transformer here, that one is actually, it does a bit more work, so I'm just going to copy-paste the others from the solution directly, so it's faster. Right, so for the time transformer, we load all our dates into a datetime object. Here you see that we're actually multiplying the timestamp by a constant value because they were not given in the right format. So that allows you to get 3 timestamp objects, the deadline, the created date, and the launch date. And then we can start creating a bit more creative features. So that's some nice feature engineering here, where we say, well, what we care about really is how much time there was between when we launched the campaign and the deadline that you had. So here we can easily compute it as a number of days. And same thing, how much time you spent between when you created the page and the launch time of your campaign. So let's look at this one. So that returns 2 nice columns with that information. And then the last one, which is if you wanted to group together some countries as groups, for example. So here I've created a map where I'm saying, well, all those countries should go in the following groups. And that's a fairly simple one where with pandas, I'm just calling the .map method to map all of those together. So here, country transformer, it returns this. If I do .sample, it should be better. Yep. And here you've got all the groups. Right, so that's for custom transformers. Next, we will look at a bit more advanced thing. So one really cool thing that was added in scikit-learn 21, so the latest version, is the column transformer. So how many of you have used that before already? Okay. So it's really useful, and so it allows you to map different transformers to different to the columns that you're interested in. So that allows you to say, well, this specific transformation should be applied to, say, all my numerical columns. This specific transformation should be applied to all my categorical columns. And that allows you to start creating rules on what transformation should be applied to what part of your data frame. So here's an example. We've defined some numerical columns, so the age and the salary, some categorical columns, the country and the gender, for example. And we create a new object. We say that's a column transformer. It takes a list of tuples, and in that tuple, you'll have 3 different elements. The first one is the name you want to give it. The second one is the actual transformation, and the third one is the list of columns to apply it to. So here I'm saying, well, I want to apply PCA not on my whole data frame, but only on those numerical columns, and I want to apply one hot encoding on only those columns. So that's really powerful if you combine it with what we've seen before. So you can start building transformations and decide, then put them all together in one single object that maps them to different parts of your data frame. So using all of that, you're able to build a master processor object that does all the transformations at once and memorizes all the states that it needs to. So that's a more visual example here, where we're doing the same thing as I explained. So we apply PCA on the numerical columns only. That's where we get in the new data frame, and we apply one hot encoding on the categorical columns only. And then the column transformer will just work as a normal transformer. So once you've created that object, you can call .fit on some training data. It will learn the internal state for all the transformations that you've provided inside it. Then .transform will apply that on any new data. So of course, you can do it on your training data, but you can do it on some test data that you want to process. Or later on, you can do it on some new data that you need to generate predictions for on the fly. So it's a really nice tool. Another one, pipeline, that is older, allows you here not to do things in parallel like the column transform will do, but sequential operations. So for example, you might want to scale some data first and then apply some PCA transformation on it. So pipeline, you'll just call the pipeline object, again, pass a list of tuples where you define what is it that you want to do. So here, I want to create an object called scaler that scales my data, and then PCA. So here, all those transformations will be done one by one on all the columns that you've got available in your data. So .fit on the data, then .transform. So that's how it will look like. So if you combine those two, you can already anticipate that you can start building pretty complex pipelines by having this pipeline that does sequential operations, and then the column transformers allows you to map it to specific columns only. So it can be used together with the column transformer. So here, that's an example of that. Here, we're going 2 steps. So we're first creating a pipeline object that we want to use only for our numerical features. So that pipeline object is first scaling the data, then applying some PCA transformation on it. So that's our first transformer. And then we build a top-level column transformer object that applies this specific transformation that we've created on the numerical features only. And then for the categorical features, it applies one hot encoding. Right? So you can start building more complex transformers this way. So the great thing here is really this second point, is that you're making everything really modular. Like every sort of operation, every functionality of your code will be a separate class, a specific transformer that does something specific really well. You can test it later, and then you're just building pipelines by combining them together. So that allows you to keep your code quite clean. Here, the only thing we are missing so far is the predictive model part of our code. Well, actually, that's not completely true, because pipeline can be used for transformers, but it can also be used combined with a predictive model. So if you use as a last step of your pipeline not a transformer, but an actual model that has a .predict method, the pipeline will automatically inherit that predict method and be able to generate predictions on your data directly. So that means that you can do something like that. So you'll have your processor that we've mentioned before, which here is a column transformer object that does something on the numerical columns and does something on the categorical columns. And then we put that inside another pipeline that has a preprocessor stage. So that's your first level here. And then a second level, which is whatever algorithm you want. So here we've chosen a decision tree. The great thing about that is that your model isn't just an algorithm anymore. And all your hyperparameters are not just on your model anymore. So it's not just about choosing the best parameters for your decision tree. It's about choosing the best parameters for all your preprocessing steps together with your final algorithm, the decision tree here. So maybe changing the values that you have in the components that you keep in your PCA will affect the best parameters to choose in your decision tree. So it's normal to have all of those tuned together and trained together. So here that allows you to do that, to represent a model as not just an algorithm, but a bunch of pre-processing steps plus an algorithm at the end. And that's also really good to avoid data leakage, because you'll have all the steps run on any batch of data you provide. So if you're doing cross-validation, all the pre-processing steps, everything will be done only on that single batch that you're providing, instead of leaking some information potentially from other batches if you did the pre-processing before the cross-validation. And you can easily apply that pipeline to any new data. Once you've managed to train it, it's just a matter of calling .predict, and it will go through all the pre-processing steps plus the predictive part. And finally, yeah, it's more modular, so it will be much easier to test and maintain. So we've got an exercise for this as well, which should be fairly short. So maybe let's take 5 minutes for you to take a look. So here, it will be in the model.py file where we've defined functions that put all our transformer objects together. So here, the first one, the most important one, is the function that builds the model. So here, two first steps that we're providing, it creates a pipeline for our categories that we've extracted with that categories extractor object. So what it does is that it first calls our transformer, and then it calls the one-hot encoder to create dummies out of that. And we also have another pipeline that is for the country transformer. So same thing, it's just creating dummies out of the categorical features. So those are just the steps that are provided. Then the exercise here is to create a column transformer object that has all the steps we want. So it will have this one, it will have the category processor, it will have the country processor. It needs to have as well the time transformer and the goal adjuster. Yeah? So yeah, if you take a look for the next 5 minutes, and then I'll go through it. All right, so let's do that part together now. So the first step here is to create your main column transformer object that will basically put everything together at this stage. So we'll just create a new column transformer. Have I even imported it? Yep. So I'll do preprocessor column transformer. So here I need a list of tuples. So the first one will be for my categories. So here I will just apply the cat processor, and I've got a list of my categorical. Oh, so here, this one is just the column category, right? So here my categories are actually extracted from only the category column. So if I provide this processor, this transformer object, only the category column, that should be enough. Then I will need countries. There will be my country processor, and I just need the column country there. Then I will need to use this. What else I got? The goal adjuster that needs the goal column and the static USD rate column. So I'll call that, how did I call it in the solution? I call it goal. So that will be the goal adjuster, the goal adjuster. And that will need the goal column and the static USD rate. And finally, I want as well the time transformer. So here, I'll call that, did I call it time? Yeah. Call it time, apply the time transformer, and I will need those two columns, those three columns, so deadline, created that, and launch that. Deadline, created that, launched that. Right, so, still missing one thing. So that's for the preprocessor object. So that, now I've got my preprocessing stage. Now I need to put it together with some predictive model. So I'll just call it, I'll call model. There will be a pipeline where I basically have two stages. So preprocessor will be my preprocessor that I've defined just above. That's my first stage. And then my second stage will just be some algorithm. So let's call it model. And here, I think I've already imported the decision tree somewhere. Yeah. So let's just do a decision tree classifier with just default parameters for now, because we're going to tune it anyway. So did I do something wrong? Is it going to work? Doesn't work. Oh, I need to return it. That would be good. All right. Category. Is there no category? There is category. Oh. It needs a list. Let me check. Oh yeah, I need to pass everything. Okay, that's my fault. I need to pass everything as a list here. Okay. Right, and now it's working. So that's pretty cool here, because we've got all our model now can be built with this single function, and we can return a new instance of our model, including all the steps that it needs with one single function. So here, that's quite easy to change the pipelines if I want to. The last step creates a preprocessor with all the things, all the features that I need to build, and the really last one puts it together with some algorithm. So here, from a top-level point of view, I just need to instantiate a new model, calling that function. I can fit it on some data, and then I call predict, and it works just like any algorithm, even though it has all the preprocessing steps included to it. Right? So next, let's go back to the slides. Right, so now we've got everything we need to build the model, and we're ready to start thinking about training it and tuning it and all of those. So here, the first thing that we'll need to think is how when we're training our model, that's something that can take a while. And when we're generating predictions, we need somehow to be able to load a model that we've trained previously. So here, we will want to be able to save somehow that model on disk and be able to, our trained model on disk, and be able to load it later to use it, say, if you want to use it in production, just to generate predictions. You don't want to retrain it every time. So here, that's what model persistence will mean. So there are two main ways of doing it with Python, of serializing objects. So you'll have pickle, that is quite well known, and joblib, that is a bit less known today, pretty much equivalent in terms of performance. In their documentation, joblib says that they tend to be more efficient with larger arrays. So we might prefer that for working with pandas and NumPys, with objects that work with pandas and NumPy. Something cool with joblib is that the interface is just a bit easier to use. So that's how you'd pickle your model using the pickle library. So you'd have to open a file in binary, then dump it, and then open the file again in binary and load it if you wanted to do that. With joblib, it's just a bit easier, because they abstract from you the loading the file in binary mode. So you can just call joblib.dump. Here you've got your model, so that's your single object pipeline that has been trained, that has you have guaranteed that it has everything you need in it. And then you specify your file, and it will just dump the whole object on that file. And then later on, if you want to load it, it's really easy. You just call .load and pass the path that you want to load. Just keep in mind it has some limitations. So pickle and joblib will just pickle that specific object that you're specifying, which is why actually it's important to have one single object. But it does not save the dependencies. So it will not. You will still need the code that it relies on to run. So that means all the libraries that it's calling, but also your custom classes, everything. You will need the files to be able to run it. Also, the data is not saved. So if you need to retrain your model, you also need to make sure that you have snapshots of your data. Other thing to keep in mind when you're using those libraries is that the versions are really, really important. So since it's relying on whatever libraries you've got installed when you're loading the model, if it has been saved with different versions, then it can often have some problems. So it's really important here that you're keeping track of what versions you've pickled your model with, and make sure that whatever environment you load the pickle from will have the exact same versions and dependencies installed. And the last comment here is that, yeah, you can pickle anything, any object in Python. So make sure that you don't load some pickle that has been provided by in some places that you don't trust, because it could contain anything, including some scripts that mess up everything. So keep that in mind. So we've got an exercise for that where we are going to here implement the last. So we only need 3 things now for our model to be able to run it on the command line. So we need a method to tune it, we need a method to train it, and we need a method to test it. So we've got all of those here. So yeah, we've got time. So let's take another 5 minutes to look at that. So here it should be fairly easy. You only need to, for tuning, for example, you will need to call your function that builds a new instance of the model. That gives you a new instance. Then you need to you can use grid search directly on it. So grid search supports the pipeline objects. So here what we have done is define in a config.py file your grid parameters. So you can uncomment that or just come up with your own parameters that you want to tune. So here, for example, we're saying that we want to tune the max depth of the model stage of the pipeline. So here the max depth of the model stage will be the max depth of our decision tree. We want to tune the min sample split of that decision tree as well. So model __, the name of the attribute in the decision tree. And then we also want to tune some of the parameters of our preprocessor object. So here our preprocessor object, we can change use all from false to true. So those are a few examples. If I do that, actually I can just give you tips. So if you do model.getParams, that gives you all the parameters that are in your pipeline object, in your model. So that tells you all the steps that you've got there. Should I zoom in a bit more? All the steps that you've got there. So it's quite a big one. If you do .keys, it tells you all the parameters that you can tune there. So that's where you see that. So you've got the things on your where is it? You've got all the parameters that are on your model. So like class weight. So all of those are defined on my decision tree. So I can tune all of those, but I can also tune everything that is defined on my preprocessor. So that's the one that I've chosen to tune here, right? So you can access all those parameters and provide them in the grid search. Actually, it's maybe better if I just do it straight away. All right, so let's just do it together. So here, first step for tuning the model is, well, load the data. So I'll load xtrain, ytrain, load dataset. Do I have the load dataset here? No, it's up there, yeah. Load datasets, and I want to load. Okay, I'll just copy that part from here. Xtrain, ytrain, okay. Right, here we are. So first I load the training data, then I'm instantiating a new model. So I'll do build model, and then I can call grid search on it. So have I loaded the grid search? Yes, I have it there. So I can define a new grid search object. Here there will be gs equal grid search CV. I pass my model directly. I will pass the parameters that I've defined in config. So I'll first uncomment them. This I don't want to uncomment. Oops. Okay. So now I go here. I import all of those grid params, and I can start using them. Okay. Here I'll do CV equal, say, 3, and underscore jobs equal -1. Then I do GS that fits on X train, Y train, and I can just print best score will be. So here you don't necessarily want to print. Maybe you want to actually get those parameters and automatically retrain your model with those parameters. But to keep things simple, I'll just do it like this. So best score, let's see if that works here. So if I call that, no. I need to import as well X train, Y train. Right, so now it's tuning my model. Yep. And here it's telling me the best score. I can also add it to tell me the best parameters, best params. Tune it again. And now it tells me as well what are the best parameters that I've got in, not in my algorithm only, but in my whole pipeline. So it's telling me that actually I should use max depth of 9 in those parameters for the decision tree, but also it's answering my question that I had at the beginning of this tutorial, which was, should I use all the categories that I get from the data frame, from the category column, or should I use only a subset of those? Well, here it's telling me that I should use all instead with those parameters of the tree. So that's quite nice. That allows you to add some extra parameters to tune in there. So we'll do the same for training. So for training, we'll need those two first. Then we'll do model.fit xtrain ytrain. So that's quite simple here. And then the last step is to save it onto a file. So we'll do joblib dump. We'll save, just have one single object to save, which is our model. And let's give it a name, model.joblib. So here, I do not have a model.joblib yet, so I can see if it worked. If I run that, xtrain train. If I run that, oops, still not, import joblib. No, because I commented out, creating traps for myself. And I trained it, and you see that it has saved it here. Well, it's a binary file, so I can't open it. But it has saved it on this, so I'm able to load it later. And actually, that's the next exercise, loading that and generating predictions. So here, test model. I'm just going to load directly model.joblib. That would be my model. Then I need to load some data as well, so I'll use that here. But it's not xtrain, it's xtest, ytest. And I need to import that as well at the top. Right. So once I've got that, now I can easily just compute accuracy score, classification report, anything I want. I just do ypred will be equal to model.predict xtest, and then I can just do print accuracy will be format ytest ypred. can try that here. That's the wrong one. Here it is, right? So here, oh, my bad, accuracy, score, all right. Right, so now I'm also able to easily test my model, and I can add classification report to that if I want. Nope. Okay. Right, and now I've got the classification report as well. Right, so that's quite nice. Now I've got pretty much all the code I need properly modular and separated, so I can easily make modifications. So I can modify the existing transformers that I've got here in this file by changing the way, say, I'm computing the category or I'm computing anything here. I just need to focus on the transform method inside my class. If I want to add an extra step, I just create a new transformer. I can test it individually, making sure it works fine. And then in the model.py, I just need to add it here in the build model as an extra step. So either I have to create a pipeline object or I add it directly to my top-level column transformer. If I want to change the algorithm I'm using, it's quite easy as well to do here. And then I'm just modifying the parameters that I want to tune to correspond to my both algorithm and steps, and it's all I can do all of that together. Go here. So also providing some command line tool out of that, because it's easier to just run it directly from the command line instead of having to start the shell and call the commands, the functions yourself. So here we've just defined a run.py that does, it basically imports our three main entry points, so the tune model, train model, and test model, and then just use the argparse library in order to have that as arguments on the command line. So if I test that now, I do cd exercise, and yes, I zoom in. Here, if I do Python run.py, say tune, that will tune my model, as it says, and tell me what the best parameters are. Maybe. Yeah. So here, you can retune it easily. So every time you make a new step, you're changing the steps in your code. You actually don't have to go through the notebook anymore. You can just run it here and see how that improved your cross-validation score, and how what are the best parameters that you should use when you train your final model. I can also do train if I want to train my model again and save it as a joblib serialized file. And then whenever I run the test, I can see the final value of my score, classification report, anything I'm interested in, really. And we could implement another entry point that would be for predict. That could be predicting loading the serialized model and generate predictions on any new data that you provided. So that would be the command you would use if you use that model in production. Right. So a few comments, things that I've skipped a little bit. So first, it's quite important. So we're going to be loading data that will change. Sometimes you'll have large training data sets. Sometimes you'll have a single row. So here it can be quite risky to just rely on pandas inferring what type your columns should be. So it's really important to whenever you want to make it to make maintainable version of your code to use to fix the D types. So that's what we've done here. We've just specified the D types for all the columns, and whenever we're actually loading the data with that function, that's why I've provided that function. here, we make sure that every time we load the data, we specify the same D types. That way, we're sure that something won't break because some data has been loaded, has been inferred as a different type than it was. Important to have a requirements.py as well, so .text, sorry. Since we are serializing our model and we're expecting our model to work in the future, it's important to make sure we can replicate exactly the same environment over and over again. So requirements.text with the actual versions of the library will help you doing that. If you're making incremental changes, make sure you're checking the score in the tuning steps, so the cross-validation score, and not the score on the test set, because that would obviously be massive overfitting to do that. So just do all your feature engineering using the tuning cross-validation score. And yeah, the really cool thing is that this is quite modular, so you can easily write tests. So that means you really should. Now it's quite straightforward actually to just take all those transformers in isolation and build tests for it. And actually that's what the next section is about. And with all of that, hopefully your updating your test should be your model should be less stressful. To finish, we have a booth somewhere tomorrow, so just come say hi. That's it. I think we've got 5 minutes for questions, if you have any. Yep.
Does it only work with pandas, or also you also use NumPy?
Yeah, you could use NumPy. So it relies on. So the question was, does it work only with pandas or with NumPy as well? So yeah, since like all of the transformers from scikit-learn accept either a NumPy array or a pandas array. Here it turns out that the actual transformers that I've built, I'm using some pandas method. So my own code will not work with pandas with NumPy. Oh yeah, you need to specify the column there. Yeah, so it's not this one is not going to work with NumPy because it's relying on you specifying what column it should be, but the rest should do. Yeah. Any more questions?
Yeah. So with the pickle or whatever the other one was called.
Joblib.
Yep. So you mentioned a couple of limitations. Is there any other way to store a scikit-learn model?
To store the model?
Yeah. So we say I train a model and then I pass that to someone else.
So here, that's actually the recommended way on scikit-learn, on their documentation they're using. So they don't have a custom way of doing it. They're using pickle and joblib, which are like just generic Python ones. If you wanted to store data, just the data, pandas has a binary format that they're using, so you could do that. But the model itself, not really. Yeah. Cool. Coffee time then.